Hello, welcome to the video of session 5 of module 2 Fast Fourier Transforms Algorithm, which is prescribed for the subject Digital Signal Processing for the 5th semester Electronics and Communication Engineering students. First, let us see the learning objectives of this session. Here, we will be considering radix 2 FFT algorithm. Then, we will be mainly concentrating on decimation in time FFT algorithm. We will going to learn this DIT FFT algorithm in depth. Then we will be considering the computational complexity which is involved in our DIT FFT algorithm. Then we will be considering some of the illustrative example for finding DFT using DIT FFT algorithm. So now first, as we considered in the previous session, in the classification of finding DFT or computing DFT, first they we classified into DFT as a linear filtering as well as divide and conquer approach. In that divide and conquer approach, which gets classified into three types, that is radix 2 FFT algorithm, radix 4 FFT algorithm, and split radix algorithm. Okay, in that radix 2 FFT algorithm, we considered again the classifications radix 2 DIT FFT algorithm as well as radix 2 DIF FFT algorithm. So here there are two, that is DIT FFT algorithm and DIF FFT algorithm. Okay, in this session we are mainly concentrating on radix 2 decimation in time FFT algorithm. Decimation here refers to splitting or dividing the sequence. As in this particular radix 2 decimation in time FFT algorithm, we are considering the signal which is in time domain and we are splitting or we are decimating in terms of time signals. Okay. So here first consider the length of our x of n, whatever the signal for which we need to find DFT, we consider the length of that particular sequence is n. That is our x of n is having n number of samples. Okay, and the n whatever we consider is a power of 2. That means n is equal to 2 power nu. So here the n in point DFT is first divided into 2 n by 2 point DFTs. Then the n by 2 point DFTs are again decimated into 2 n by 4 point DFTs. And this decimation will going to continue until the 2 point DFTs are obtained. That means the minimum number points of decimation will be till 2 point. Furthermore, we will not going to decimate. Once we get the 2 point DFTs, we stop. So we are splitting the complete n values till we obtain 2 point DFTs. Okay. Now let us consider the length n sequence which is x of n. That means our x of n is having the samples x of 0, x of 1, x of 2 up to which is x of n by 2 minus 1 up to x of n minus 1. Okay. Now if we split this x of n, that means if we are decimating this x of n into two sequence of length n by 2, that means we are dividing the n point samples or length n sequence into two length n by 2 sequences. So what we obtain is how we are decimating or how we are splitting is we are considering the sequence which are having even indexed values and sequence which is having odd indexed samples. So observe, even index sequence what we got here is x of 0, x of 2, x of 4 up to x of n minus 2. Similarly, odd indexed sequence. So our odd index sequence is having the samples x of 0, x of 1, x of 3 up to x of n minus 1. Now, if we consider endpoint DFT of the sequence x of n, which is x of k, which is given by the equation x of k is equal to summation n varying from 0 to n minus 1 x of n into w n raised power of kn for the value of k varying from 0 to n minus 1. So there are n values or n samples in x of k. So now if we decimate or if we split our time domain signal x of n into even and odd index sequence, what we obtain is x of k will be divided into summation n varying from 0. So it is from even value to n minus 2 into x of wn raised power of kn plus summation n varying from 1 to n minus 1. So it is odd x of n into wn raised power of kn. Okay. If we substitute the value of n as is 2r, okay, in this first term, let us substitute n is equal to 2r, and in the second term, let us substitute n is equal to 2r plus 1. Okay, what we obtain is x of k will be equal to summation r is varying from 0 to n by 2 minus 1 x of 2r into wn raised power of 2kr plus summation r varying from 0 to n by 2 minus 1 x of 2r plus 1 into wn raised power of k into 2r plus 1. Okay, which is equal to summation r varying from 0 to n by 2 minus 1 gr into wn raised power of 2kr plus summation r varying from 0 to n by 2 minus 1 hr into wn raised power of k into 2r plus 1. So now using the property of twiddle factor, wn raised power of 2 is equal to wn by 2, we can write our x of k, the DFT x of k as summation r varying from n by 2 minus 1 gr into wn by 2 raised power of kr plus wn raised power of k into summation r varying from 0 to n by 2 minus 1 h of r into wn by 2 raised to the power of kr. So here observe this particular uh, terms. So with the first term represents the DFT of GR, as well as the second term represents the DFT or n by 2 point DFT of H of R. Okay, so we can write this x of k as g of k plus omega n raised power of k into h of k. Here the value of k in both this first and second part is varying from 0 to n by 2 minus 1. We can observe here both our g of k as well as h of k are having n by 2 point DFTs. So these two n by 2 point DFTs constitute one n point DFT x of k. So now our g of k, as these are n by 2 point DFTs, the g of k and h of k, so they are periodic with n by 2 points. Okay, so g of as they are periodic with n by 2, how can we write? Our g of k is equal to g of k minus n by 2. Similarly, we can write our h of k is equal to h of k minus n by 2. Okay, so for our value of k, which is varying from n by 2 to n minus 1, that is last half, can be written as x of k is equal to g of k minus n by 2 plus wn raised power of k into h of k minus n by 2 for value of k varying from 0 to n minus 1. Okay, now let us consider the value of n is equal to 2 per nu, where our value of k is varying from 0 to 7. Okay, so from equation what we obtain, what we have written is x of k is equal to g of k plus wn raised power of k into h of k. Okay, for the value of k varying from 0 to n by 2 minus 1. Okay, so we can write x of 0 as g of 0 plus w8 power 0 into h of 0. That means for this value of capital N as 8 we are considering, and and we are considering the values for this x of k value is varying from 0 to 7 here, but here it is from 0 to 8 minus 8 by 2, that is 4 minus 1. So 0 to 3 we are considering. X of 0 is this, Similarly, x of 1 is g of 1 plus omega 8 power 1 into h of 1. X of 2 is equal to g of 2 plus omega 8 power 2 plus into h of 2. Finally, x of 3 is equal to g of 3 plus w 8 power 3 into h of 3. So, from equation that is x of k is equal to g of k minus n by 2 plus omega n or w n raised power of k into h of k minus n by 2. Here, the second half, where the value of k is varying from n by 2 to n minus 1. So, we can observe here, this is the first half, 0 to n by 2 minus 1. Here it is n by 2 to n minus 1. So, we can write our x of 4 as g of 0 plus omega 8 bar 4 into h of 0. X of 5 is equal to g of 1 into 1 plus w 8 bar 5 into h of 1. X of 6 is equal to g of 2 into w 8 bar 6 into h of 2. Similarly, the last one, x of 7 is equal to g of 3 plus omega 8 bar 7 into h of 3. So, this is how we can represent our DFT for first half as well as the last half. So, this is how we have split it or we have decimated. So, after first stage of decimation, we can write the flow graph for the value of n is equal to 8 as, see, we can observe here. We have considered the values from x of 0 to x of 7, which is converted or which is decimated into 2. So, as we considered n is equal to 8, obviously this n is equal to 8 is decimated into n by 2, 2n by 2, that is 2 4-point values, g and h. G is 4-point DFT and h is again 4-point DFT. So, we can observe here. Next, what we will be doing is, again we are considering g of r and h of r which are from x of n. Okay, x of n we decimated into g of r and h of r as considering even and odd index sequence. Here again we are considering g of r and h of r separately, and again we are decimating by considering even and odd indexed sequences. Okay, and after dividing, if we obtain their DFTs, what we obtain is g of k is equal to a of k plus w n by 2 raised power of k into b of k, where our value of k is varying from 0 to n by 4 minus 1. Similarly, g of k is equal to a of k minus n by 4 plus w n by 2 raised power of k into b of k minus n by 4. Here the value of k is varying from n by 4 to n by 2 minus 1. So, this represent first half, that means even indexed, and this is for odd index, second half. Okay, this is for g of k, that is g of k is nothing but n by 2 point DFT of g of r. Similarly, next we will be considering h of k, which is n by 2 point DFT of h of r, that we are splitting again. So, h of k will be can be represented as c of k plus w n by 2 raised power of k into d of k, where the value of k is varying from 0 to n by 4 minus 1. Similarly, h of k is equal to a of k minus n by 4 plus w n by 2 raised power of k into b of k minus n by 4. Here our the value of k is varying from n by 4 to n by 2 minus 1. Why we are writing this is, as we know, our g of k and h of k are n by 2 point DFTs. As they are n by 2 point DFTs, they are periodic with n by 4. Okay, so we can write like this. Okay, now, so this is how we can decimate it. This is this second stage of decimation. So after this second stage of decimation, for n by 8, we can write the flow graph like this. See, this is from the first stage of decimation, and this is from second stage of decimation. We can consider here. Okay, so in the first stage, we decimated our x of 0 to x of 7 into 2 n by 2 point DFT is g of 0 to g of 3 and h of 0 to h of 3. Okay. Now we are dividing this g of k as well as h of k into 2. That is a of 0 to a of 2, a of 1, and b of 0 to b of 1, as well as c of 0 to c of 1, and d of 0 to d of 1. Okay. So the computation has been reduced to a computation of 2-point DFTs after second stage of decimation. Okay. So the 2-point DFT, what we got here is A of k, which is given by summation n varying from 0 to n by 4 minus 1, which is x of n into Wn by 4 is power of kn. Here the value of k is varying from 0 to n by 4 minus 1. So our A of k is representing n by 4 point DFT. Okay, so if we consider the value of n as 8, obviously our A of k represent 2-point DFT. Okay, so our A of k is varying from summation n varying from 0 to 1, x of n into W2 raised power of kn, where our value of k is varying from 0 to n minus 1. Okay, so now let us consider A of k is equal to summation n varying from 0 to 1 x of n into W2 raised power of kn, where our value of k is varying from 0 to n minus 1. Here, for value of k is equal to 0, so for value of k is equal to 0, A of 0 is equal to x of 0 plus W2 raised power of 0 into x of 4. And for k is equal to 1, A of 1 is equal to x of 0 plus W2 raised power of 1 into x of 4. Okay. So if we write this n by 2, that is 2-point DFT, by considering x of 0 and x of 4, we obtain A of 0 into A of 1. So A of 0 is equal to x of 0 x of 0 plus W2 raised power of 0 into x of 4, and A of 1 is equal to x of 0 plus W2 raised power of 1 into x of 4. So using that blocks, we can write the complete flow graph for DIT FFT algorithm for the value of n is equal to 8. So this is how we can write. So in the first stage of decimation, x of 0 to x of 7 is converted into two 4-point DFTs, g of 0 to g of 3 and h of 0 to h of 3. So g of k and h of k. So x of k is n-point DFT and g of k and h of k are n by 2-point DFTs. So after second stage of decimation, g of k is converted to 2 n by 4-point DFTs, that is A of k and b of k, and h of k is converted to 2 n by 4-point DFTs, c of k and d of k. So this is how the complete flow graph represents this decimation in every stage. So we can consider here 3 stages of decimation. Okay. Each block here we will be calling as a butterfly because it resembles the structure of butterfly. We call that particular operation as butterfly operation. Okay, the input data here are not in the natural order. Natural order means as we are considering the input data sequences, the time domain sequences x of 0, x of 1, x of 2 up to x of n. Here the input we are giving is not in that natural order. Instead, it is in bit reversal order. We are going to check this in the next slide. Okay, why it is not in normal order, we are going to check in the next slide. Okay, so the endpoint DFT, whatever we are obtaining from this DIT FFT algorithm appears in normal order. That means what we need to concentrate here is input whatever we are giving is not in the normal order, and but we are obtaining the output, that is DFT of the x of n, that is time domain sequence, will be in normal order. So what as we are not giving the inputs in normal order, that means which is not in the order. So how exactly it is we are providing is it is in bit reversal order. because of the repeated decimations. As we saw in the previous slides, because of the repeated decimations, the input sequence is scrambled. Okay, it gets scrambled, and the order of the final input sequence is will be in different form. Okay, so we're going to see how this we can going to obtain. Okay, so we can observe here input sequence here x of 0, x of 1, x of 2 up to x of 7. So index of this input sequence is 0, 1, 2, 3, 4, 5, 6 and 7. So if we represent this input sequence which is in normal order in binary form, we obtain 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 up to 1, 1, 1. Now, if you consider this input sequence which is in normal order, in the normal order, okay, in the binary form, and if we reverse the bits, okay, reversing the bit means we are making the MSB as LSB and LSB as MSB. Okay, so 0 0, if we reverse order also we will get the same 0 0 0. If we reverse 0 0 1 we obtain 1 0 0, and if we reverse 0 1 0 we obtain same order 0 1 0. If we reverse 0 1 1 we obtain 1 1 0. If we reverse 1 0 0 we obtain 0 0 1. If we reverse 101, we obtain the same order 101. If we reverse this 110, we get 011. Last it is 111. If we reverse, then also we will get the same thing. So we are representing this index in decimation. We obtain this 0, 4, 2, 6, 1, 5, 3 and 7. Final output sequence order what we obtain is x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. So this bit reversal order sequence we are giving the input, giving as input to the DIT FFT, that to 8-point DFT FFT DIT FFT algorithm. It's not just giving this one. For giving this particular input, we have to have some algorithm called bit reversal order algorithm, and we have to that bit reversal order algorithm has to be supported by the addressing mode. So our digital signal processor supports this bit reversal address mode, okay, where that can be calculated just by, if we consider this 000, if we want to find out for 8-point DFT, then 8 by 2, that is n by 2 point value has to be added. So if we add this, and if the carry is propagated to the next level, in natural addition, what how we will be doing is, if we add this LSB to MSB, our carry propagates. But here we have to consider carry propagation from MSB to LSB side. Okay, and then we have to have the values. Okay, so this is how we can implement bit reversal order addressing mode. Okay, and our uh, uh, digital signal processor supports this bit reversal order with the specific addressing mode as well as the some architectural features that we will going to see in our higher semesters. Okay, another beautiful or useful thing in our DIT FFT or FFT algorithm is in place computation. Here you can observe. So this is representing a 2-point DFT or a butterfly operation of a 2-point DFT, where we are giving these two inputs xm of p and xm of q. Output whatever we obtain is xm of x of m plus 1 into p, x of m plus 1 into q. Okay, this xm plus xm plus 1 of p is equal to xm of p plus wn raised to the power of r into xm plus 1 into q. This xm plus 1 of q will be is equal to xm of p plus wn raised to the power of r plus n by 2 into xm of q. Okay, so this two represents outputs and these two represents input. Okay, since the value of this particular twiddle factor Wn raised power of r plus n by 2 is can be written as Wn raised power of r into Wn raised power of n by 2. Since we can represent this as minus 1, simply we can write it as w minus Wn raised power of r. So using that, how can we represent this is x of m plus 1 is equal to p is equal to same thing, but the second term we are replacing by xm plus 1 of q is equal to xm of p minus Wn raised power of r into xm of q. So this is how we can reduce the computation. So this represents addition of these two. This represents subtraction of these two. Okay, same thing. So this gets reduced to this particular operation. That means multiplying these terms every time will not be will be reduced or will be completely taken off. Instead, this will be multiplied by minus 1. Okay. So xm this xm plus 1 of p is equal to xm of p plus wnc. Here we can see our twiddle factor wn raised power of r into xm of q. Our xm of plus 1 of q is equal to xm of p minus wn raised power of r into xm of q. So if we consider any of the butterfly calculation which involves two complex inputs, so these two are the complex inputs to this particular butterfly structure, and two complex outputs. Obviously, because of these two complex input values, we obtain these two complex outputs. Once these outputs are calculated, yaudu, this xm plus 1 of p and xm plus of q are calculated, these inputs xm of p and xm of q of the butterfly are not used in any other calculation. So further we will not be requiring these values. So what happens, whatever the storage space we used to have this xm of p and xm of q before can be used to store this xm plus 1 of p and xm plus 1 of q. That means this memory space will be replaced for storing these two values. So this is how we can use in-place computation. That leads us to have the reduced memory requirement. So this is the main advantage of our FFT algorithm. The same thing is applicable for the DITFF, DIFFT algorithms. So our xm plus 1 of p and xm plus 1 of q can be stored in the same memory locations as the inputs xm of p and xm of q. So this is called the in-place computation. Okay, just by considering the reduced butterfly operation, the complete reduced flow graph for n is equal to 8 can be represented or written as like this. Okay, so we are having 8 parallel lines and 3 stages of decimation. For n is equal to 8, we have 3 stages. For n is equal to some general value, n raised power of new stages of decimation we are going to have. See, each stage is having n by 2 butterfly operation. You can observe here. Here value of n is equal to 8. So 4. N by 2 is 4 butterfly operation. 1, 2, 3, 4. 1, 2, 3 and 4. Here also 1, 2, 3, 4. So 3 stages of decimation. Each stage is having 4 number of butterfly operation. Input to this is given in bit reversal order and output we are obtaining in natural order. So you can observe here the complete reduced flow graph for n is equal to 8 for the DIT FFT algorithm. So computational efficiency, let us consider direct computation. In direct computation, number of complex additions are n into n minus 1. Number of complex multiplications we are going to consider are n into n, that is n square complex multiplication. If we consider the radix 2 computations, the computation number of complex additions will be reduced to n into log n. Okay, obviously it is lesser compared to our direct computation method. Number of complex multiplications are n by 2 times log of n. Okay, so percentage saving in addition is given by 100 minus number of additions in radix to FFT divided by number of additions in direct computation of DFT into 100, and percentage savings in multiplications is equal to 100 minus number of multiplications in radix to FFT divided by number of multiplications in direct DFT, okay, into 100. So now let us compare the computational complexity involved in direct method as well as in using DIT FFT algorithm. We can see here, see these are the number of stages, okay. These are number of points. This represent number of complex multiplication in direct computations. Here number of complex multiplication in radix 2 DIT FFT. Here number of complex additions in direct calculation of DFT, and this represent number of complex additions in radix 2 DIT FFT algorithm. So for n is equal to, nu is equal to 2, n is 2 power nu is 4. So for finding 4-point DFT, in direct computation method, 16 complex multiplications are involved, and in DIT FFT algorithm, 4 complex multiplications are involved. In direct computation, there are 12 complex additions. In DIT FFT, there are 8 complex additions. We can observe here 16, here 4, 12, 8, reduced. If we consider 32-point DFT, 1024, it is 80. See, for 32-point DFT, 1024.24 number of complex multiplication. It is just 80 complex multiplication in DIT FFT. 992 number of complex additions in direct computation, but it is just 160. If you consider, see, if we are finding this, how many values? See, 1024-point DFT. Observe how many are there here. 1 million complex multiplication. In case of direct computation, it is just 5120 in DIT FFT. We can observe the greater reduction in complexity, computational complexity. Here also it is also around 1 million complex addition that gets reduced to 10,240 complex additions. Okay, that is why we are going for radix to DIT FFT algorithm for finding DFT. So for understandability of this particular DIT FFT, let us consider some of the illustrative example. First, what they have given is, they have given 4-point sample x of n, that is 0, 1, 2, 3, and they have asked us to find DFT x of k. So let us solve this. Given value of n is 4. So we have to find the twiddle factor. W4s per of 0 is 1. W4s per of 1 is minus j. DIT FFT algorithm for n is equal to 4. We can write it as, we can observe here, we are giving the input in bit reversal order. This is not in natural order. X of 0 is 0. X of 2 is 2. X of 1 is 1. X of 3 is 3. Okay. We are giving input here. First, after this first stage, we obtain 2, minus 2, 4 and minus 2. And the output of the first stage is taken as input to the next stage. So the final output, whatever we obtain, is 6 minus 2 plus j2 minus 2 minus 2 minus j2. So DFT of the given sequence x of n is x of k, which is equal to 6 minus 2 plus j2 minus 2 minus 2 minus j2. Now let us consider 8-point DFT, finding 8-point DFT. What they have given is x of n is equal to 2 power n, where n is varying from 0 to 7. So there are 8 values in this x of n, and we have to find the value DFT, x of k. So let us start. As they have given the value of n as 8, and we have to derive the values of x of n, 2 power n. We have to substitute value of n from 0 to 7. So 2 power 0 is 1, 2 power 1 is 2, 2 power 3 is 4. This is how we need to generate this sequence x of n. So x of n is equal to 1, 2, 4, 8, 16, 32, 64 and 128. Okay, we require the 4 values for the twiddle factor W of W8. So W8 power 0 is 1, W8 power 1 is 0.707 minus J.707. W8 power 2 is minus J. W8 power 3 is minus 0.707 minus J.707. So by substituting these values in the butterfly structure, we obtain this one. So we can observe here the input we are giving here is in bit reversal order. You can observe here not as x of 0, x of 1 and x of 2. Instead we are giving it as x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, x of 3 and x of 7. Along with the corresponding values we have substituted the inputs here. After first stage of calculation, we obtain the outputs 17, minus 15, 68, minus 60, 34, minus 30 and minus 120. So this is the second stage of computation. Output of the first stage now will be considered as input to the second stage. After the computation here of the second stage computation, we obtain the outputs as 85, minus 15 plus j 60, minus 51, minus 15 minus j 60, 170, minus 30 plus j 120, minus 102, minus 30, minus j 120. So we have to take this output of the second stage computation as input to the third stage or last stage of the computation. After finding or after performing the third stage computation, the final output we will be obtaining in natural order. So our TFT x of k for the given input x of n, what we obtain is x of 0 is equal to 255, x of 1 is equal to 48 minus 64, 48.63 plus j times 166.05, x of 2 is equal to minus 51 plus j times 102, x of 3 is equal to minus 78.63 plus j times 46.05, x of 4 is equal to minus 85, x of 5 is equal to minus 78.63 minus j times 46.05, x of 6 is equal to minus 51 minus j times 102, x of 7 is equal to 48 minus 0.63 minus j times 166.05. So we can write x of k as whatever the value we obtain here, 255, 48.63 plus j 166.05, minus 51 plus j 102, minus 78.63 plus j times 46.05, minus 85, minus 78.63 minus j times 46.05, 51 minus j times 102, 48.63 minus j times 166.05. So this is the 8-point DFT of the given sequence x of n. So summarizing, so in this session, hope you understand all this concept. What we considered here is we started with the concept of radix to FFT algorithm. So in the radix to FFT algorithm, there are two types, that is DIT FFT as well as DIF FFT. So in this session, we mainly concentrated on decimation in time FFT algorithm. So we took to how we derived, how to derive the DIT FFT algorithm just by considering the value of n is equal to 8. That means for 8-point DFT, we derived the decimation in time FFT algorithm. After that, we considered the computational efficiency. That means we compared the computational complexity of finding DFT using DIT FFT algorithm with that of finding the DIT FFT algorithm using direct method. Afterwards, we considered some of the illustrative example for finding DFT using DIT FFT algorithm. Hope you understand all the concept that we tried to explain in this particular session. Uh, for further reference, you can refer to the books written by Prokis and Monolokis in their work, Digital Signal Processing, Principles, Algorithms, and Applications. And you can also refer to book written by Li Tan and Jean Jiang in their book, Digital Signal Processing, Fundamentals and Application. Also, you can refer to the book written by Mr. Uday Kumar S. in his book, Digital Signal Processing. And for the session, you can refer to the links which we have, and you people can refer to the stuffs or things which is related to this particular session through these links. Okay, you can access to this video with this link, and this session PPT can be accessed using this particular link. You can see the multiple choice questions using this link, and you can check for the notes of this session using this link. Thank you all. And this is the LMS team, and please appreciate the effort. Thank you very much.